Hello anatomy students. In this lecture video, I'll talk to you about the cardiac cycle and how the actions of the heart push the blood through the different chambers of the heart and also how they make the heart sounds. So let's get started. The first thing I want to talk about are the heart sounds. When you hear your heart beat, you hear a lub-dub, lub-dub, lub-dub. So you have two sounds that are occurring. They're called S1 and S2. So the first sound that you hear is S1, and the second sound that you hear is S2. And the characteristics of the first sound is that it's louder and it has a little bit of a longer sound, whereas the sound for S2 is softer, it's sharper. Now, a lot of times people will say that it's caused by the valves, but and that's only partly true. The valves don't slap each other and make a sound like a door that slams into the door jamb. So like the flaps themselves are not making the sounds. But when the flaps of the valves move, they create turbulence in the bloodstream. And it's that turbulence as it knocks against the walls of the chambers of the heart and as it knocks against the flaps that form the valves, that's the sound that is creating these heart sounds. So the valves themselves operate silently. Oh, but the heart sounds coordinate with the closing of the valves. So the first sound, lub, coordinates with the closing of the AV valves, whereas the dup is going to coordinate with the closing of the semilunar valves. So this is a picture of the cardiac cycle, and I just wanted to point out that one cardiac cycle is happening every 0.8 of a second. So even though it's going to take me about 15 or 20 minutes to go through this, this is happening in less than a second. You can see that we have 4 different phases of the cardiac cycle, but I do want to call your attention to the fact that the very first phase, ventricular filling, takes up 2 blocks. So it includes the blue block and the green block, and there are 3 different parts to that phase. So let's take a look at what's happening in each of these. And there are a couple of things that you need to focus on, which I put on the note sheet on the very first page. You need to focus on where is the blood flowing in each phase, and which valves are open and which valves are closed, which chambers are in diastole and which chambers are in systole, and how does each of these phases correspond to what you see on a normal ECG. And then we're also going to explore how pressure differences in the chambers of the heart are going to allow this blood to flow. All right, so let's get started with ventricular filling. Ventricular filling is phase 1, but it actually occurs in 3 different parts. Like I said before, it takes up 2 blocks on the graphic, the blue and the green ones. The blue block, the first 2 parts, include rapid ventricular filling and diastasis. And diastasis is just a fancy term for like the slowdown of the filling. So what's happening here is that the blood is coming in through the superior and inferior vena cava and entering into the right atrium. The blood is also flowing in from the pulmonary veins from the lungs and filling the left atrium. And then notice the black arrows that we have on our picture that's showing you the blood flow. And the blood is just passively filling our ventricles. And so the very first part, you have this happening very quickly, and then it starts to slow down a little bit, and it's going to occur at the end of the P wave, which I have pictured for you on the slide. The third and final part of ventricular filling is called atrial systole, and you should remember that systole means that the cardiomyocytes are contracting. And if you take a look at the pictures that I have on the slide, in the green picture you see the little lines on the outside of the atria. So those are the little squishy lines that are showing you that the atria are starting to contract, and you can see that the actual shape of the atria here have changed from what they look like in the blue picture. And so the atria are contracting and they're pushing the blood through the AV valves and into the ventricles. So at this point, in the green box, your atria are in systole, your ventricles are in diastole, so those are relaxed, and you have the AV valves open. At this point, you have a higher amount of pressure in the atria than you do in the ventricles, and this should make sense. When you decrease the volume of a container, you are increasing the pressure within that container. And so as the container of the atria decreases because they're contracting, they're becoming smaller, now that's going to rise the pressure up and force the blood through the AV valves and then into the chamber that has a lower pressure. Remember that substances are going to move from areas of high pressure to areas of low pressure, so they're moving down their pressure gradient, and so that's what we're seeing here with the blood. Okay, phase 2 is called isovolumetric contraction. And you'll see on my ECG here that this is occurring where the S point is on our ECG. And you're probably like, well, wait a minute, like what happened to like the QR line of the QRS complex? Well, that did happen, but just remember that in order for the cardiomyocytes to contract, they have to be stimulated first. So the ECG is going to be a little bit ahead of what's happening in the heart muscle itself. And so yes, the QRS occurred, and it's causing the contraction of the cardiomyocytes in the ventricles, but the actual isovolumetric contraction isn't happening until point S. So now let's explore that term isovolumetric. So iso is the prefix that means same. Vol means amount, or in this case, volume, and then metric is measurement. And so this is the same measurement, and what this means is that the amount of blood that is in the ventricles is not going to change during this phase. The amount of blood that is in the ventricles at the end of atrial systole, it's called the EDV, or the end diastolic volume. The EDV is not going to change during isovolumetric contraction. So what's happening is that our cardiomyocytes that are in the ventricles, they're starting to contract, but not enough to increase the temperature, to increase the pressure in the ventricles so much that the blood is going to be ejected from those ventricles. What does happen, however, is that the blood surges up. Note the black arrows that we have in the picture. And as the cardiomyocytes in the ventricles contract, the blood is starting to be pushed upward, and that's going to cause the AV valves to be pushed closed. So the blood is kind of pushing on the bottom side of those valves and causing them to close. And so the pressure is building in the ventricles, and so it's going to be higher than the atria, causing those AV valves to close, but not high enough to open up the semilunar valves in the pulmonary artery and in the aorta. So those valves are going to remain closed. And as I have here in yellow, the ventricular pressure is less than the pressure in the blood vessels. And by blood vessels, I'm referring to the pulmonary arteries and the aorta. So here we've got the AV valves are closed during isovolumetric contraction, and the SL valves are closed. The semilunar valves are closed, and that's happening in both the right and the left sides of the heart. So whenever you have the term isovolumetric in the name of the phase, all the valves are closed. They have to be. Otherwise, the blood is going to be moving and it's not isovolumetric anymore. Phase number 3, the orange box, is called ventricular ejection. And so as you can see in the picture, you have the squishy lines on the outside of the ventricles, and the ventricles are beginning to contract. But now these cardiomyocytes are contracting so much that the pressure in the ventricles has exceeded the pressure in the blood vessels in the pulmonary artery and in the aorta. And so now that blood is being pushed through those valves, and it's going out of the ventricles and into the pulmonary artery from the right side of the heart and into the aorta from the left side of the heart. So here we've got ventricular pressure has now exceeded the blood vessel pressure. This part of the cardiac cycle corresponds to the plateau, which is found in the action potential trace for a single cardiomyocyte. And the plateau is the flattened area at the top. Remember that it's caused by this inflow of calcium ions into the cardiomyocytes, and it's going to allow the cardiomyocytes to remain depolarized for a longer period of time and allow them to remain contracted for a longer period of time too, which is really important in this phase, because you want to give the ventricles enough time to contract and to push the blood out of the ventricles, as much blood as possible, out of the ventricles and then into the great vessels. Notice that the ventricles are going to be contracting from the apex towards the base, so from the bottom up. And just remember that, the cardiomyocytes in the heart are arranged in like a spiral, like they're kind of forming around the heart. So when these cardiomyocytes contract, the heart is going to contract from the bottom, from the apex where this hand is, and as it contracts, it pushes up, and then when it relaxes, it comes down. And when it contracts, it twists, it pushes up, and then it comes down. And that's going to allow for the ejection of the greatest possible volume of blood from the ventricles. I also want to mention that late in this phase is when we have our T wave. So here we've got ventricular depolarization happening late in this phase. So even though this phase is ventricular ejection and we have ventricular systole here, the T wave, that electrical signal, is happening first, so that in the next phase we're going to see this ventricular diastole, which is caused by the T wave. All right, and here we are. Our final phase is called isovolumetric relaxation, and there's that term again, isovolumetric. So you should remember that if it's isovolumetric, the volume of blood in the ventricles is not changing, and in order for that to occur, all of the valves in the heart have to be closed. So the semilunar valves are closed. You have the AV valves also closed. Here we have ventricular diastole. We're coming upon the end portion of our T wave. And so our ventricles are relaxing and they're expanding. And so if the container, the ventricles, are expanding, that means that the volume is increasing. And if you increase the volume, you decrease the pressure. The pressure in this phase is not enough. It's not lower than the atria. So these AV valves are going to remain closed. And still we're going to have our SL valves closed. Now this is a really important phase, especially for the cardiomyocytes themselves, because this is the phase where they receive oxygenated blood. All right, so I'm going to try and do this gracefully on camera, but this is obviously a model of the heart, and the great vessels are here at the top, and this large red one, this is the aorta, and it sprouts off of the left ventricle. And the other important arteries that are going to sprout off of my aorta are two coronary arteries, the right coronary artery and the left coronary artery. And they sprout off of our aorta here, and then they're going to branch off and serve the right and the left sides of the heart. remember that the blood that's actually inside of the ventricles and the atria, that blood doesn't directly serve the cardiomyocytes. The blood has to enter the right and left coronary arteries in order for the heart tissue to be perfused. And it's during this phase that oxygenated blood from the left ventricle enters the aorta, and then the blood is going to come back down. So let's just talk about that a little bit. So during this phase, during isovolumetric relaxation, as I said, our ventricles are going to relax and the pressure in the ventricles drops. And when that happens, the blood is, any blood that's left in our aorta, is going to fall back down. Again, just from the force of gravity, it's just going to pull that blood back down. And when it does, it's going to fill the cusps that create the semilunar valve and push them down and force them closed. And those cusps are going to fill with blood. And so what I did is I took off the top of the heart in this model. Now I'm going to show you this view. So what we're looking at here, this large opening that you see with the blue vessel, this is the pulmonary artery, and above it, this is the opening for the aorta. At this time, the aortic valve is closed, and you can see that there's these little cups here. So when the blood comes back down, again, from the force of gravity and just like by the fact that the pressure in the ventricles is dropping, the blood is going to come back down, fill these little cups, and force the valve closed. And as the blood pools inside of these cups, you can see that we have some dark spots right here, and then there's another one on the other side. And so these dark spots represent the openings for the right and left coronary arteries. I'm trying to find the other spot there and show it to you, but trust me, there's definitely two of them that are in there, but there's one of the spots. And so when the blood pools inside the cups of these valves, the blood is going to drain into that hole, and then it's going to travel through, in this case, the left coronary artery, and then down to the front of the heart where my fingers are kind of moving, and then around also to the back. So this is an important phase in the cardiac cycle for our cardiomyocytes, because this is kind of when they get their supper. This is when they get oxygenated blood and nutrient-rich blood from our systemic blood flow. So it's during this phase, it's when the ventricles relax and the blood, especially in the aorta, it's happening also, in the pulmonary artery, but remember, that's deoxygenated blood, so that's not going to go into the coronary arteries. So we're talking specifically about the aorta here. So the blood in the aorta comes back down, forces the valve closed, the blood pools in those cups, and it drains into the right and left coronary arteries, and then it's going to kind of feed the heart muscle cells. And so once again, just remember that during this phase, all of our valves are closed, so that like any blood that's left in here is just going to stay in there. So there is going to be some residual blood volume that remains here with each heartbeat, but it shouldn't really be that much. All right, so that is the end. That's the last phase of the cardiac cycle. And now it just kind of goes back to the very beginning, and it's going to start with rapid ventricular filling, and then diastasis, which again is the slowdown of the ventricular filling. Then you have atrial systole. You have isovolumetric contraction. You have ventricular ejection, and then you end up with isovolumetric relaxation. I hope that you found this video helpful. Let me know if you have any questions. And this will definitely help you fill out the cardiac cycle lecture note sheet, but then also the cardiac cycle activity packet that I handed out in class. Thanks for watching.